All right, let's go. So in our solar system, we have a bunch of gas giants and ice giants and rocky planets, which I'm sure you're all perfectly aware of. But we don't find anything between the gas giants and the ice giants, and that's what this talk is all about. How we can distinguish these types of planets using radial velocities and transits. So thank you, Charles, for setting the stage for transits being useful as well, is that we can look at their bulk densities. So between the gas and the ice giants, we have different densities. And of course, also it's more extreme if you go to the rocky planets. But I see this bulk density as a manifestation of the core mass fraction of these two different types of giant planets being different. So that's our solar system. If we look at exoplanets, we find that we have many super Earths and mini Neptunes, which seems to be the most like normal common planets out there. And then our ice and gas giants would lie down here in the x-axis on this Kepler statistics plot. So when we do look at other exoplanetary systems or other planetary systems, we do find some of these transitional objects that are falling in between being an ice and a gas giant. And they're found to be common to around 7% if you look at transiting planets within 100 days of their star. If you look for the same type of planets using microlensing, yeah, I just realized we haven't really spoken much about microlensing this conference, not so surprising, I guess. But here it's basically the same as the Kepler statistics plot. On the x-axis, you just have the mass ratio of the planet to the star instead of the size of the planet. So if I plot, if I put in my ice and gas giants, that's sort of around the mass ratios that they would lie, because most of the planet hosting stars in microlensing will be M dwarfs. So we can make some assumptions that they're all more or less the same mass. And then the different curves you have on this plot is quite busy, I'm sorry, is what we measure in microlensing, that's the red line. And then we have in the two blue shaded areas what we predict from planet formation models. So these are the burn models with and without migration. The takeaway from that plot is though is that what we measure in microlensing is not the same as what we predict. So if we take a step back and try to figure out why do we predict not having that many transitional objects, let's say it like that. We can look at the core migration accretion as very standard, like old school planet formation theory, but I think some of these points still hold up, and that's basically what I want to test in this talk. So I'm gonna speed through this real fast, so stay with me. So we start out with creating a planetesimal that will then accrete somehow. I think pebble accretion is sort of what most people will subscribe to these days until you reach a pebble isolation mass. Then over time, your envelope will contract up until the point where you have so much mass in your core that you have a runaway gas accretion effect. And the way I think of this effect is that either when you're creating a gas or giant planet, either you will create something that's Neptune-like, or you will reach this critical mass for the core to then get runaway gas accretion effect. So if we believe in this very, let's say, toy model of planet formation, giant planets should either be Jupiter-like or Neptune-like. And I'm really talking about them in terms of their bulk densities here, or like the core mass fraction. So that is the experiment that I'm gonna talk a little bit more about today. So we had a look at the TOIs from year 1. So this is something that started quite a long time ago. That's why it's year 1. Now, of course, if I was repeating this experiment, I could look at many years of TESS data, but this is what we had available back then. So what I plot here is the planet radius for the TOIs as it was back when we were deciding on our target. Oh no, it's from last year. Good, I updated it. Very good. So these are the different TOIs, and then they're color coded depending on sort of what the disposition is within TFOP. So if it's a good planet candidate, or if it's already a confirmed planet, and so on. And just to let you know that there are still quite a lot of candidates within this range, but there's also a lot of false positives. We use HARPS and Corelli to follow up these targets. And I'll say a little bit more about why we chose these two instruments, but just to sort of set the stage that HARPS is on a 3.6 meter telescope, and it was the state of the art in terms of radial velocities for many years, and can reach quite routinely 1 meter per second for bright stars, whereas Coralie is on a smaller telescope. It's 1.2 meters, and we're sort of limited to 3 meters per second when we're photon limited. So I want to quickly advertise that the Swiss group has this a very nice website that's called DAYS, where a lot of these radio velocities will be uploaded. And we did a big data release, I think around 1.5 years ago, of around 1,300 spectra of TOIs that are all publicly available now. And as far as I know, the plan is to continue making some of these follow-up data publicly available. So if you are interested in using some of these data, do contact the Geneva group or myself. So just to remind everyone that when we are looking at these transitional types of planets in mass and radius, we are looking at something between 4 and 10 Earth radii. So they're quite large, but they're really spanning an order of magnitude in terms of that mass. And we don't always really know what kind of mass we're gonna expect when we start observations. So normally we would start with Coralie, and then if the semi-amplitude of the radial velocity seems to be small enough, we will then continue observing with HARPS. So I think there's a really nice synergy in this project between two different spectrographs. And that's one of the things that I want to highlight is that even though I think it's very fun to use these like the best facility out there and the most state-of-the-art facility out there, I also think that more modest radial velocity precision still plays a very important role in follow-up and can really help us get the most out of our more pristine facilities as well. So, all right, we have time for some radial velocity curves. Very good. So just to give you some examples of some of the targets in our sample, TOI 181 is my personal favorite. It has a really nice TESS light curve, so we obtain a quite good precision on the radius. It's a 6.2 Earth radii, so like smack in the middle of this transitional radius regime as I've been talking about, plus minus 0.2 Earth radii. It has an orbital period of 4.5 days. And then we find the mass with Coralie and HARPS that I've shown here. And the star is active, and we don't have tons of data. So using a GP on it is a little, maybe overkill is what I would, so I haven't included any slides in this, but that's something I'm happy to discuss with other people. But we're sort of trying to look into how to treat the activity so we get an accurate mass, but without sort of overfitting. Another very nice system is TOI 880, where we found the first transiting planet. That's the one I show on the top panel here. Right, from the first year of TESS data, then TESS went back to the southern hemisphere and re-observed the system, and we found 2 additional transiting planets. So that means that, of course, all of these things take a little bit longer to follow up when you keep finding more and more planets. It makes them very interesting, of course, but it also makes it a little bit more time consuming, which is why this paper is still in prep. But just to let you know that we can get the mass of the inner and the outer planet, and then the middle planet, we can only get an upper mass limit for as it is right now. The star seems to be quite inactive, let's say it like this. So it's quite easy to deal with. All right, I'll wrap up, Jen. So just to let you know that we're about to publish these 11 systems that we've been following up where we can confirm the planets, and we will of course also publish our false positives. And I think what's quite interesting when you look at the plot here, so this will sort of be our updated mass radius relationship, is that first of all, they all seem to follow a quite tight mass radius relationship. So this is another thing that we will look into for the paper, is to really go through all of these transitional type objects and maybe double check if we can refine the mass on some of the other targets that fall within this range. And then also a lot of our targets turned out to be multi-planet systems. So this could again tie back to maybe some tidal inflation. So that would fit with all of them being sort of puffy Neptunes, let's say like that. So with that, I'll leave up my conclusions. I think the most fun part of this project will be to do the population study. And then I will, because we're all like gonna go away from this conference thinking about the next conference. So I'll make a little advertisement for this ESO conference on spectral fidelity that will be in Florence this September. And then I should end this talk saying that all of this work was done in collaboration with the Coralie team and the Geneva team, though I am now currently at ESO. So thank you very much.
Wonderful, thank you. Okay, we have time for a quick question. So any hands in the room? No, there we go. You beat you by half a second.
So I'm really glad that you're investigating these interesting transitional objects. Have you noticed, can you comment on any of the preliminary trends in age or metallicity? These sub-Saturn objects, like last time I checked, seem to be preferentially around younger and active stars and also around metal-rich stars, which is kind of interesting.
I think like it's very hand wavy. I will see that it does look like a lot of our targets turned out being young on the younger side, even though we were not going for younger active targets at all. So there could be something there. And this is what I'm interested in at the moment, is following up young planets. And that basically came from this project because a lot of our targets just turned out to be young and interesting. So.
Okay, let's thank Louise one more time.